Welcome to an introduction to exercise 16, Evidence of the Earth's Revolution from Astronomers as Observers and Experimenters, published by Kendall Hunt. I'm Professor Jeff Wilkerson at Luther College. And I want to just provide a little bit of an introduction to this exercise, one of my favorite exercises in this laboratory book. It's a challenging exercise, without a doubt. It's one of the exercises that my students struggle with year after year, but struggle is good as we try to pull things apart, try to understand the work that we do. And so the struggle comes from a couple of different places. One is, so let's start with the idea. So the idea is this, that if you've got a star out here, and this is not to scale, of course, let's at least expand it out. So you've got a star that's way out there. It's really way, way, way out there. And here we are orbiting the sun. That there will be a time, if everything's in the plane of this board, and everything won't be, but if it is in the plane of the board as we've drawn it, there will be a time when we directly approach that star and when we directly recede from that star. If that star were not moving relative to the solar system, relative to the sun, if that star is not moving away from us or toward us, then we would see a blue shift here, and we would see a red shift here. And the speed, the V over C, is equal to delta lambda over lambda, where delta lambda is the shifted wavelength, lambda is the unshifted wavelength, the rest wavelength. Then we would see this velocity would be the velocity of the Earth in orbit. Okay? The lambdas that we're looking at, the waves that we're looking at, are absorption lines in the spectrum of this star. All stars, except Wolf-Rayet stars, all other stars, those aren't very common, all more typical stars have dark absorption lines in their spectra. And this is what we show you here in the exercise. You see the dark absorption lines. This part of what we're dealing with right here, A and B, you see the dark lines in this. So that's the data right there from the stars. A is taken at one time. Let's say here, I don't know which one's approaching, which one's receding, and B is there. So you get a spectrum 6 months apart. So those spectra are taken 6 months apart, and you can see the dark absorption lines in there. The bright lines across here are from reference lamps, emission lamps in the observatory. And so the bright lines are the unshifted. You can get if you find the wavelengths of these bright lines right here, if you find the wavelengths of those bright lines, that's your lambda. And if you can find the corresponding dark line in here, then you can use the corresponding dark line and find the wavelength of the dark line, and then lambda dark absorption minus lambda bright is going to be delta lambda. You can get that shift. We do everything in this activity in angstroms. It's a little bit of an old-fashioned unit. If you want to do this in nanometers, by all means, go ahead and do this in nanometers and just multiply everything by 10. So this is your finder chart. Do all of your measuring on this, the actual data. This is just a finder chart to help you identify those bright lines. You see those 3 bright lines? That's those 3 bright lines. You see that sort of doublet line right there? There's that doublet line, doublet line, doublet line. So you can say, that line right there has a rest wavelength of 4,260.48 angstroms, or 426.048 nanometers. So you can get the wavelength of the line from here. Don't measure on here. Don't take your ruler. Don't take your caliper and measure on here. Measure up here on here. Do all your measuring here. Do your line identification down here. Okay? So that's what we want to do. We can get delta lambda here. Delta lambda over lambda gives us V over C, and we're great. We've placed this exercise in the measuring in the solar system section because we're using that to measure the velocity of the Earth. We can say the velocity of the Earth is equal to C times delta lambda over lambda, except it's not that simple. And we could have placed this in the stars and galaxies section of the text. Nothing's ever that simple because that star's moving as well. And we can measure the velocity of the star as well. Now imagine that the Earth's not moving, or here's an idea, here's a way to picture this. Imagine that the Earth is here in its orbit moving that direction, neither toward nor away from this star. At that moment, we would just measure the velocity of the star. Excuse me. We would just measure the velocity of that star. And we would then do the exact same thing. We would look for the wavelength shifts like we just talked about, and we would use that and apply there and say, in that case, at that point, we're measuring the velocity of the star to be C equals delta lambda over lambda. But we don't typically, we could do that. We could definitely do that, and we should, it would be a great way to do that. We wouldn't be able to do it on this side because it would be up during the daytime. On this time, it would be in opposition at that point that we've drawn right here, if this is the sun, and at that point in our orbit, and that would be a great time to measure the speed of the star. And we could do that. We could, instead of measuring the velocity at 6-month intervals, we could measure it at 3-month intervals, and the one halfway in between would give us the velocity of the star. We don't do that typically. We might, but it's expensive to get spectra. It's hard to get spectra. You could be observing something else, and you have enough data here to pull out the velocity of the star. What you have to recognize is, imagine that this star is, as I've drawn that arrow, which I drew that arrow to mean it's very far away, but imagine that star is actually receding from us. It may or may not be receding from us, but if it is receding from us, then it is also adding redshift to this data. So the star is redshifted. And if the star is receding from us and you see a redshift, that means here the Earth is receding from the star. And here the Earth approaches the star. Okay? When the Earth is receding from the star, if the star is receding, remember the star might be approaching or it might be receding. If it's receding, then Earth's motion is causing a redshift, star's motion is causing a redshift, and you get a big redshift. Not big, but bigger redshift than you would from either one of these things independently. So the two things add. So in that case, where you have these two things adding like this, you can say, oh, when I measure at this point, I'm measuring the velocity of the Earth plus the velocity of the star to be equal to c times delta lambda over lambda. Well, that's great. Okay, now, but you've got two unknowns, one equation. You need another equation, two equations and two unknowns, and you can solve for these two unknowns, but you've got it over here. At this point, the Earth is making a blue shift spectrum, but the star's still making a redshift. If the star's receding, it's always receding. If the star's approaching, it's always approaching. Okay, unless it's part of a binary system, but we'll worry about that some other time. So if here the Earth's motion is causing the spectrum to be blue shifted, here the Earth's motion, the star's motion is causing it to be red shifted. So the two are pulling in different directions. They're causing different shifts. Okay, if they're causing different shifts, if the Earth's speed, I want you to picture this for a moment. If the Earth is in orbit faster around the sun than the star is receding from the sun, then that means the Earth's velocity wins. We're actually approaching that star at that point because our velocity is faster than the star's velocity. Star's running away from us. So picture yourself in a race and you're running after somebody. They're running away from you. But if you're running faster, then you're catching up. And that would be the case with us here, and we would see a blue shifted spectrum. So we would see a blue shifted spectrum and a red shifted spectrum. The blue shift would be smaller because in the blue shifted spectrum, it's blue shifted from the Earth's velocity, but it's red shifted from the star's velocity, and we would have the velocity of the star is equal to c delta lambda over lambda. There's our two equations and two unknowns. Now, it's possible, in fact, it's likely in many cases, that the star's recession velocity is actually faster than the Earth's velocity, in which case you would still have a red-shifted spectrum. You have a red-shifted spectrum here from the Earth receding from the star and the star receding from the Earth, and here you would have a red-shifted spectrum. The Earth is approaching the star, eating away some of that redshift, but the star's redshift is so great it can't eat it all away. Now you're in that race. You're running after a person, but that person's faster than you are. That person's pulling away from you still. Even though you're running toward the person, they're pulling away from you. That would be the case if the star's receding more quickly, in which case we would actually have V star minus V Earth is equal to c delta lambda over lambda. In either case, you've got two equations and two unknowns. And you can go out there and you can do whatever you want to do with these two equations. You can add them together, and you'll see that some of the terms go away. You can solve one of the equations for one of the terms and plug it in over here. You've got different approaches there. Sometimes I like to just say, look, I've got one value minus another value, And then I've got the one value that I started with plus that same value. So here I've got my value, I add something to it, and I subtract something from it. And it's the exact same thing that I'm adding that I'm subtracting. Can I picture where if I take v sub e and I add v sub star to it in one case, and I subtract v sub star to it in the other case, where does v sub e fall relative to the two numbers that are over here? So this is lambda, let's say b, b, a, a. So this is number sub b and number sub a. Where does it fall to the number between, where does v sub b fall relative to number b and number a, like that? And so I like to picture that sort of thing and see, but that's for you to practice, and that's for you to get a sense of processing this data. Lots of learning goals we can approach in this activity. Careful measurement is certainly one of those, but understanding how fast a star is moving, understanding how fast the Earth is moving, all of these are interesting things to be working on. The careful measurement bit of that learning goal. Before we get into that, I'll come right back to that, but before we get into that too far, recognize that this could be, again, I don't know if A or B. This is A or B, and you call it B or A. One of these is A and one of these is B in there. And it's also possible, we did this, we talked about this for the Earth, the star receding. The star could be approaching. And if the star is approaching, then it's adding a blue shift always. And in this case, it would be added to this spectrum over here, where both of them are giving us a blue shift, and the subtraction would occur over here, where the Earth's giving a red shift. So you just flippy-floppy all of this around. That's a technical term, okay? Flippy-floppy is a technical term for the changing around what we did over here. So any event, this is what you've got going on. In terms of the careful measurement, these measurements are actually tricky to do. And I definitely recommend you do these with a digital caliper if you have a digital caliper available to you. And the way I like to do it, it's your data set. You can use it however you want to use it and approach it. The way I like to approach it is to pick the three dark lines in the spectrum here that are easiest to identify and easiest to figure out where the edges or the centers of the lines are. And you can see, so if you can identify those lines, work with those lines, and I'll give you a little tip here. Pro tip, I just love that line right there. So that line right there, I think those dark lines are easy to see. They're relatively narrow. Unlike some of the lines in here, I can identify that dark line and that dark line, the dark line in spectra A and B, are associated with that bright line. The bright lines are the same in A and B. And you see the dark line shifted left or right relative to that bright line, but the line's relatively narrow, unlike some of these lines where they get washed out and they're really kind of tricky to measure. So I would identify three of these lines that are the easiest to measure. And what I do is I take a straight edge and I place it right along here, and I draw a pencil line, a thin pencil line that runs down through both spectrum A and spectrum B. And then I measure to see how much that dark line is shifted left or right from that pencil line. And that's telling me how much this dark line is shifted left or right from this bright line. And that gives me the shift in my spectrum. But that's the shift in this picture of the spectrum. This picture is like a scale model of the spectrum. We could have printed this picture tiny. That would have been not very much fun for you if we printed the picture this big and you had to try to measure these shifts. Or if we could have printed this in a fold out, we could have made this piece of paper fold out this direction, and we could have made it twice as big, right? We could have had it twice as big, folded out this direction, and so the actual number of millimeters, for example, that these things are shifted left and right, depend both on the wavelength shift, the delta lambda, and the scale of our model, the scale of the picture that we've printed here, which we call the dispersion of the spectrum. So you need to determine the dispersion of the spectrum, and really what I would do is just pick two bright lines that are widely separated, easy to identify, measure the space between, say, those two bright lines, bright line, measure the space between those two bright lines, always measure on the data up here, and then just read the wavelengths off down here. And when you read the wavelengths off, that sets the scale. It says, oh, a shift of this many angstroms is equivalent to a shift of this many millimeters. Shift of this many angstroms, 4,307.91, for example, minus 4,260.48, that's a shift of that many angstroms. A difference of that many angstroms in your data is equivalent to this many millimeters in your data. And so then you can calculate the dispersion of your spectrum in angstroms per millimeter. Think of it as the scale of the picture. You're setting the scale of the picture right here. Angstroms per millimeter sets the scale of the picture. And so you've calculated the dispersion of your spectrum. You multiply by that number. You measure your delta lambdas in millimeters. Multiply that in by millimeters, and you've converted your delta lambdas to angstroms. So you've converted from picture space to wavelength space to say we've got a picture of the spectrum, but we want to know what that means in actual wavelengths. And to convert from picture space to wavelength space, we have to multiply by this angstroms per millimeter conversion. So there's a good little bit of data processing and thinking about all the different pieces and all the different levers that you have to pull to do good data processing here. It's tricky data to measure on this spectrum. The shift is so small, but you get interesting information out the other side. So this is a great example of the care you have to take to go through to get interesting information to come out of the data sets that you're looking for. And so I love this exercise for doing that. But it also then leads us, one of the things that we do a lot here, and as we work through here, is to try to think geometrically, to try to think about the geometry of the solar system, the geometry of the galaxy, the geometry of the universe. What can we do from our observations to think geometrically and to say, okay, we talked right at the beginning of this long rambling introduction to this exercise about this star lying in the plane of the board, but the star probably doesn't lie in the plane of the board. It's probably up here or behind the board someplace. So that means we're not moving directly toward it. In fact, if this is the sun, if this is the solar system, and it was straight above the solar system, we wouldn't move toward it or away from it at all. And so now, in the discussion questions at the end, we want you to work through thinking about where that star would have to be on a star chart, for example, for it to be where we would be approaching it directly or receding from it directly, and how might we correct for that if it's out here a little bit. If it's out here just a little bit, we're still mostly moving toward it. Less toward it, less toward it, less toward it, less toward it, not toward it at all. Toward it away a lot, not at all. And so you see that geometry as this thing moves around. Is it possible to correct for that? And if again, it's your exercises. I talk about this a lot in these videos. It's your exercise. You will adapt it to do what works best for you, and to think about, what trigonometry do you know, what geometry do you know, how much math do you want to do to try to do this. But this is a one that you can work through that direction and think about a little bit that way. A good exercise to really think about how we take data analysis and convert that into deep knowledge of how the universe works. So I hope you have fun with it. I hope you're challenged by it a little bit. That's how we grow, is to be challenged by things. And I hope you come out the other side appreciating the work that goes in to do something like this, and having a little bit of confidence in your ability to be able to be a part of that, to be able to not just recognize it, but to understand it at the level where you're actually engaged in this work. Have fun with it, everybody. We'll see you an introduction to another exercise.